Okay, this is the lecture that corresponds to what was done in class on Wednesday. So if you were in class on Wednesday, there's no need to watch this lecture, but this is to make up for the fact that Wednesday's lecture was not captured on Echo due to having things set up wrong both on my end and on Echo's end. So where do we find ourselves? We were previously talking about the sample mean. So in our case, that's going to be the sample mean vector. So in your mind, you should think, okay, our data looks something like what we have from the bird data, where we have multiple observations, and each observation has many variables. And so to find the mean vector, we take the vector, to find the sample mean, I should say, the sample mean is obtained by taking the sample means of the first components and the sample means of the second components and the sample mean of the third components and creating a vector. So our mean is going to be a mean vector. And our variance, well, our variance is a covariance matrix. And so we find the sample covariance matrix in the usual way, where we divide by n minus 1, and we take the I-kth component is obtained by taking all of the I components and subtracting off their difference from the mean of the ith components, and doing the same thing for the kth components and doing that cross multiplication. Of course, SII are the diagonal elements, and the diagonal elements of the covariance matrix give us the variances of the individual components. Okay, so where we were talking about sample means. Oh, and by the way, I'm just lecturing from the notes. These notes are posted on Canvas if you'd like to follow along and make notes yourself. Okay, so again, we've been talking about the sample mean and the sample covariance matrix. We're going to change for just a second and switch to population mean. And what we'd like to do is understand the population mean and the covariance matrix of a new random, well, eventually a new random vector down here that we will get to. But to set us up for that, what we are going to first consider is the one-dimensional setting, where we're going to look at the new random variable ax plus b. So we have a random variable x. It has mean mu. It has variance sigma squared. And we're going to create a new random variable by taking that old random variable, multiplying it by a, and adding on a constant b. Okay, so of course what that would do is multiplying by a would change the shape of our distribution. So if a has magnitude greater than 1, our distribution is going to spread out a bit. Adding b is going to shift that distribution. Okay, so you are familiar with how this works. If I want to find the mean of my new random variable ax plus b, then because expectation is linear, I can move it inside, and I have a times the expected value of x plus b right here. And of course the expected value of x is mu, and so we end up with the new mean of a times mu plus b. And you'll also recall how it works for variances. The constant term b does not affect the variance. It doesn't affect the spread of the distribution at all. And so the variance of the new random variable is affected by the constant multiplier a, and the way that translates into variance is that becomes an a squared. And so the new variance would be a squared sigma squared, since our random variable had variance sigma squared before. Okay, so how does this work for a random vector? So now let's change the problem. Let's let the random vector x be a p-dimensional random vector. It's going to have mean vector mu bar. It's going to have covariance matrix sigma. I'm going to use sigma rather than S because we're talking about the population. And for that matter, I'm using mu rather than x bar. So these are the true population mean vector and population covariance matrix. Okay, so how does this work? Well, here's kind of just a picture of what's going on here. What we're going to do is we're going to consider this new random vector, which is obtained by taking our random vector x, multiplying it by a matrix A, and adding on a vector B. And here I say the matrix A is a matrix which is R by P. And of course this P has to agree with the dimension of X. So that's what I've tried to show down below. If X is a P-dimensional vector, so it's P by 1, of course the dimension of A has to agree with it. And then we can have the number of rows of A be any number R. So what's going to come out of this multiplication is a R by 1 vector, and then B would of course have to be R by 1. So that's just talking about how the dimensions of these pieces would have to agree. Now what we want to do is, this is going to start with some random vector. It has some dimension, some distribution in p-dimensional space, and it's going to change that distribution. It's going to shift it by adding it by b, and then this multiplying by the matrix A is going to transform it in kind of in lots of directions, and not all directions equally. Nevertheless, we do have very easy representations of the mean and covariance matrix of this new random vector. And the way that works for the mean is really the same way. We still have linearity. This is relatively easy to show, but I'm not going to take the time to do that. So the expectation can be moved inside because this is a linear function in p-dimensional space. The expectation can be moved inside, and we just end up with A times mu plus B over here. And you'll notice that the dimensions still agree because mu would be a p by 1 vector, and so we would have essentially the same picture as we have above in terms of dimensions. The variance is a little bit different. You'll recall, of course, that we said the variance when we were doing univariate case, we ended up with the multiplier squared. The way that works for variance here is that b again does not affect the variance, but this a, we have to square it somehow, and we need the dimensions to agree. So if you think about this, I'm going to zoom in here a little bit so I can write. We said a was r by p. A transpose is going to be p by r, and the variance of x was, which is sigma over here, is p by p. And so if we do this multiplication, you'll see that we end up with a matrix which is going to be r by r, and that's what we want because we said that the random vector coming out of this multiplication would be r-dimensional, and so its covariance matrix would make sense to be r by r. Okay? So the solution is that we end up with A times the original covariance matrix, or the covariance matrix of our original random vector x, times A transpose on the other side. And you can see that's kind of like squaring by the matrix A. Okay. So from there on Wednesday, we moved into linear algebra review. We're going to be dealing a lot with matrices and vectors, and so we're going to need to know some things about linear algebra. I'm not going to review all of linear algebra in this class. I know that you have taken a linear algebra course prior to being in the MAS program, and that there was some linear algebra review done at the in kind of that boot camp. But a list of things you should know from linear algebra. Of course, you should know what it means to multiply a vector by a scalar, as we were doing, that a times x. I mean, x doesn't necessarily have to be a random vector, but you should know what it means to multiply. To do scalar multiplication, you should likewise know vector addition. You should know the dot product and the meaning of the dot product. So, of course, the dot product of a vector x times a vector y is you multiply the first component of x times the first component of y, and do the same with the second components and the third components, and then add them up. And the dot product divided by the magnitude of x and the magnitude of y gives the cosine of the angle between those two vectors. So notice we're computing the vector length there. We should know how to find the length of a vector, and of course the length of a vector is just the dot product of the vector with itself, square rooted. So just take the first element of x, square it, take the second element of x, square it, do that for all the elements of x, add them up, take the square root. That gives the Euclidean distance, or the Euclidean magnitude of a vector x. You should know what it means for vectors to be orthogonal. Essentially, if their dot product is 0, then they are orthogonal. You should be familiar with the idea of a projection. Projecting a vector A onto a vector B is given by this formula here. The dot seems to be almost missing, but it's A dot B divided by B's magnitude. So the way I sort of think of it is this part is giving the direction of B, and you're just taking A times or dot producting A with a unit vector in the direction of B, and that gives you the projection. Okay, you should know how to transpose a matrix. You should know matrix vector and matrix multiplication. You should be familiar with the ideas of linear independence, a basis for a vector space, the span of a matrix, and the rank of a matrix. And finally, you should also be familiar with the notion of inverse matrix. So if you're panicked right now, I don't know that you should be. If you, for instance, forgot the formula for projection, that's okay, but you should be familiar with all of these ideas, at least, to the point where if you were to look them up with, type projection of a vector in Wikipedia, and they gave you the formula, you'd say, oh yeah, that's how that works. So that's kind of the level of familiarity that should be, you should have. Okay? So the next thing we're going to do is we're going to we're going to go through a list of special matrices. And you can see that we've kind of jumped back to some older notes that form the basis of this class that I taught early on. So the first set of special matrices is it's really how to generate a matrix. So we can generate a square symmetric matrix from a rectangular non-symmetric matrix A by computing A times A transpose. That's what this sentence at the top says. So what's going on here? Well, we're going to think of A being, let's go ahead and say it's R by P, and we're going to think of R being greater than P, or at least that's the way I'm going to draw it. So here is our matrix A, it is R by P, and then my A transpose would be short and fat, and so this would be P by R. And you notice that I just threw the transpose there. So the first rectangle is supposed to represent A transpose. The second rectangle is supposed to represent A. They have their dimensions R and P. And of course, we can do the multiplication because these R's agree, and we're going to end up with a P by P matrix, which in this case would be of the small dimension, the way that I've written it. So we can see that it's square. We can also see that it's symmetric, and that's what's being done here. To be symmetric, we know that a symmetric matrix, let me just call it C. If C is symmetric, then C transpose equals C. So that's what they're showing here. You may recall that if I have the product of two matrices, A and B, and I transpose them, that equals B transpose times A transpose. So that's what's being applied here. We have A transpose times A, the whole thing being transposed. Well, applying that rule above, my first thing, my second matrix ends up being first, and that's transposed, and then the first matrix ends up being second, and that's transposed. So this second piece is A transpose transpose, and I end up with A transpose A, and we see that it is symmetric. So we can create a square symmetric matrix by taking a rectangular non-symmetric A and computing A transpose times A. Okay, that's our first special matrix. The second special matrix is an orthogonal matrix. And actually, what I'm going to do is I'm going to stop this recording because it's going to be easier to upload a little bit shorter video, and we will pick up in the next video with the orthogonal matrix.